Evening and welcome to Kung Fu Physics, where we are working our way through the practice physics GRE problems one at a time. And today got a mechanics problem for you. It's off the 1986 exam, number 76. It looks something like that. If you have it at home printed off, go ahead and flip to 76 off the 1986 practice exam so you can follow along. Now, I'm feeling a little under the weather today. I've been sleeping all day basically and just haven't felt well. So I'm hopefully not going to make a big muss out of this problem. And it is an easier one. It was near the top of my stack and I grabbed it when I saw it. It looked like an easy one, and it is. And so I guess I'll go right into it. I usually scan the answers first. And when I scan the answers for this, I notice several things. D and E are in units of energy. MGH, it looks just like a potential energy. So I know the units for those two would be energy. And then the top three are units of something else. I don't know what they are. They are different even amongst themselves, because A and B have an R, an extra R in there. So I know the units of these answers are going to be different, and if it came down to it and I was maybe going to try to eliminate something, I know I would have good chances in this problem just looking at units. So I note that, I move on quickly and read the problem, take a quick look at the diagram, and of course you scan back and you go between all these three things: the diagram, the text of the problem, and the answers. When you do these problems, you should be constantly reevaluating, looking between those three things, how they're associated with each other. Number 76, a hoop of mass m and radius r is at rest at the top of an inclined plane as shown above. The hoop rolls down the plane without slipping. When the hoop reaches the bottom, its angular momentum around its center of mass is. So we're just letting this hoop roll down and get to the bottom. You pretty much have to assume, and I guess the text of the problem says that there's no friction. Part of what it's saying, if it's saying it's rolling without slipping, is you're not getting any energy lost to friction. So the first thing that pops into my head when I saw this problem is conservation of energy. And so again, in my head, I may look at this a little bit differently than rather summing energy to zero, as a lot of people do. I look at it, in my mind, it just makes a lot of sense to look at it that the initial energy is, of course, equal to the final energy, as long as nothing is a non-conservative force sapping energy out of the system, which is the case here. So the initial energy is equal to the final energy. And the initial energy is going to be all potential. When we look at our diagram there, we see that the hoop's sitting up at a mass h, and you should check that with the diagram. Make sure they don't play a trick on you by saying, oh, h was the distance from the bottom of the center of mass of the hoop at the bottom to the bottom of the hoop at the top, or something crazy like that, where you'd have to put in an extra r, an extra radius of the hoop or something like that. But in this problem, you can see that h is actually the distance from the center of masses of the hoop. So it's the same point on the hoop that they're measuring that distance from. It's fine to use m, mass of the hoop, g, h, as our total energy that was initially all present as potential energy. Now, it gets converted into two types of energy at the end of the problem when the hoop is down at the bottom. And conceptually, you can hopefully see it in your head exactly what's happening at the bottom, how the energy is being stored. It's being stored as kinetic energy, two forms of kinetic energy. One is the translational kinetic energy, the center of mass of the hoop is moving. And two is the rotational kinetic energy, because the hoop is rotating at that point. It should be easy to imagine if somehow you stuck an axle through the thing and you picked it up off the table immediately. Of course, that thing would still be rotating. There's rotational kinetic energy in that. And of course, there's translational kinetic energy. Same thing. If it was somehow forced to not rotate and it was sliding on ice, you can imagine that that hoop would continue rotating. So they're separate ways of storing that kinetic energy that are both present. And they're related, of course. We're all familiar with how things roll, and things tend to roll without slipping, as described in the problem. So they are related. Okay, blah blah blah. Let's solve the stupid thing. So 1/2 big M v squared is our translational kinetic energy plus the rotational kinetic energy, and hopefully you're very comfortable with the thought of the equations of motion for rotational motion look very similar to the equations of motion for translational, except you just make some substitutions. Instead of the mass, you use the angular momentum. Instead of the translational velocity, you use the rotational velocity, which would be an omega. Now, I solved this problem a couple ways, actually. The first way I did it worked out smashingly, and then the second way I did it, I said, why did I do it this way? It didn't work out quite so well. And the first way I did it is actually making the substitution early on for I. This is not one of those moment of inertias that is present in the tables. It doesn't say moment of inertia for a hoop. It doesn't have that. The moment of inertia for a hoop is really easy to remember, though. It's just mr squared, where r is the radius of the hoop. And I don't know what the best way for you to remember this is, but for me, I mean, it's again, you're just summing a whole bunch of little masses, so little mass elements. If you did the calculus of this problem and you saw how you're just using parallel axis theorem to sum a bunch of these that are all at radius, and you sum it up over the whole hoop, you are going to get that, the total mass times the radius. So I don't know. You probably have worked so many problems with hoops in your day that you probably remember that anyways, but clearly you do need to know that for the physics GRE. So the I hoop equals mr squared. I put that in right here, and it seemed to work out, as I said, pretty well for me. The other thing that's important to realize is that the translational velocity of the hoop is related to the rotational velocity when something is spinning without slipping, and you get V equals R times omega, right? So whatever angle that hoop is turning through, whatever angular speed it's turning through, you know, that's in units of inverse meters, and then you multiply it by the radius. The bigger the hoop is, the more that thing is going to translate in a horizontal velocity. The more that it, as it turns, the higher the radius is, the further it's going to go. These are related. You know, you can do all the calculus again and do little differentials and see how that works, or you can just conceptually understand how that works. And so I made that substitution, and the problem worked out pretty well for me from there on. So let's just go ahead and show what that looks like. I am quite certain there are other, maybe easier, maybe better ways to do this problem, but like I said, I'm feeling ill today and I'm at the point of not caring, so we'll just do it this way, if that's quite all right. I forgot 1/2 there, and so I multiply the 2 through, divide by the m, 2gh, divide by the m. Okay, and then this got me down here where I was happy to solve for omega, actually. I was happy to solve for omega. That comes out, actually, that 2, because we have 2 of them there. Skipping steps. getting sloppy. Alright, so that was what my omega came out to. Square root of GH over R, and then I look at the answers and I say, oh no, my answer isn't there. And then of course I remember back to the actual problem. Always important to think, what are you trying to get to the end? Like I said, flipping between the text of the problem, the diagram, and the answers is important. And so I didn't panic for more than a moment, and then I looked at the problem and it says the angular momentum about its center of mass is. And so what I really ultimately wanted in this problem is angular momentum, which is moment of inertia times the rotational velocity, I omega. And so all I'm doing is multiplying I omega times this. So again, I use m r squared times root gh over r. And that gives me m r root gh. And then I'm really hoping at that point that one of those is in my answers. mr root gh. It's there. It's right at the top. Answer A. Awesome. So I would choose that as my answer. And as I said, I'm going to go right after I finish this, actually, maybe go look at some of the other solutions. There are probably other rather clever ways to do this problem. But the way I've done it is certainly a way to do the problem. So that's all for now. Study hard.